Hi, my name is Danny, and presenting alongside me today will be Kate, Antonella, and Trent. And we will be presenting our research on Pacific Northwest forestry, climate change implications, mitigation, and adaptation strategies to climate change.
Climate change is having impacts across the world and is far from projected to stop, so in order to set the scope for our presentation, I'll be going into some detail about the basics of climate change projections and the implications thereof for the Pacific Northwest. Climate scientists use what is called an RCP, or a representative concentration pathway, to map out the possible scenarios for climate change impacts in the future in relation to different amounts of effort to reduce and mitigate emission levels. What we will be looking at specifically is RCP 8.5, or the business as usual model, which assumes practically no efforts are made to limit or mitigate emissions, and of course has the most severe effects associated with it, as indicated on these figures. Some fundamental changes we will see as a result of climate change in the Pacific Northwest will be changes in precipitation and in temperature. Overall, annual precipitation and average temperature are projected to increase. These changes will have major impacts on the health of forests in the Pacific Northwest, and by proxy will have major impacts on the forestry industry.
As stated in the previous slide by Kate, the Pacific Northwest can expect a net increase in temperature. This temperature increase will be approximately 4 degrees Celsius according to RCP 8.6. The figure to the right shows which parts of Oregon will experience higher temperature changes and which will experience lower temperature changes. The darker blue areas more inland on this map represent areas that are going to experience higher temperature changes. These areas are higher elevation zones and are also expected to experience an increase in productivity. The lighter blue areas closer to the coast represent areas that are going to experience lower temperature changes. These areas are also lower elevation zones and are expected to experience a decrease in productivity.
As I mentioned previously, we in the Pacific Northwest can expect to see an increase in the annual average rainfall overall, but these increases won't help us out when we need them. The left figure exemplifies what I mean by this very well. We can see that following the high emissions pathway, we can expect to see an increase in annual precipitation overall, but if we look at the seasonal breakdowns, this will reflect a drastic seasonal difference, which will look like much wetter winters and springs and much drier summers and falls. Normally, summer drought in the Pacific Northwest is mitigated by the flow of water sourced from the snowpack that accumulates over the winter, which slowly melts to feed streams and rivers throughout drier months. Normally, with increasing precipitation occurring in the winter months, we might not expect to see such severe drought effect in the drier months, but due to warming temperatures, winter precipitation is falling less as snow and more as rain, so we don't get that snowpack accumulation, which we can see on the right figure, which shows percentage of current snowpack volume compared to historical averages. So, how do these changes in precipitation affect the forestry industry in the Pacific Northwest? Well, a lot of studies have been conducted about one of the forestry industry's favorite trees, the Douglas fir, which is favored for its fast and straight growth patterns. Due to the changes in precipitation, we can expect to see changes in the growing season of the Douglas fir. Because the growing season for the Doug fir will become much drier for much more of the time, this will decrease the amount of time that the trees can actually grow. Additionally, drought contributes to water stress, which decreases the amount that trees can grow per growing season and can also compromise the health of the tree overall. The abiotic factors of the Pacific Northwest ecosystems are shifting, and in junction with this, we can expect to see shifts in the species that inhabit them. The ecosystem that native species in the Pacific Northwest are well adapted to exist in is rapidly changing to a drier and hotter one, and the species will struggle to thrive and proliferate. Instead, species that are more well adapted to the new norm for this region will become more prevalent. A good example of this is the ponderosa pine and other species like it, which are more well adapted to drought and high heat and are less likely to experience stress symptoms as a result of these factors. As ecosystems and their corresponding demographics shift, we can expect to see changes in fire frequencies to occur in tandem. These changes are likely to occur because the species becoming more prevalent in the area are ones that rely upon fires to maintain a healthy forest, like the aforementioned ponderosa pine, of which the lower branches fall off to provide tinder for low-intensity, high-frequency fires, which are typical of their indigenous region.
As can be seen in the figure to the left, precipitation primarily enters into the tree through the roots. It is then used in combination with carbon dioxide and sunlight to create sugars that allow the tree to live and grow. In order for a tree to grow, water needs to reach the roots. Increased temperature allows plants to take up more water. However, increased temperature also means more water sticks in the air and doesn't make it into the soil. This means that although a plant's ability to take up more water is increasing, the availability of water in the soil is decreasing. When plants do not receive the water they need, their growth is stunted, they grow smaller leaves, parts of the tree may start to die off, and in extreme cases, the entire tree may die. These effects are especially seen in younger trees, which is a growing number as we cut down our old-growth forests and replant to replace them. Pathogens are extremely important to keep forest ecosystems in balance. However, when pathogens are not native or a new plant species is introduced, pathogens can set the entire forest ecosystem out of balance. The Oregon coast is a prime example of where human intervention has caused an increase in pathogen presence. Oregon has a long history of logging on the Oregon coast. Douglas firs, which are easy and quick to grow, are replanted in these logged areas. With changes in precipitation and temperature, the Douglas firs on the Oregon coast have been infected by a pathogen that historically was not a problem in these areas. This pathogen is Swiss needle cast. As can be seen in the map, Swiss needle cast has spread across the entire Oregon coast. The discoloration seen in the picture to the right is one of its most notable features. This pathogen causes the growth rate to decrease by about 20 to 50% and causes the needle retention rate to go down from 4 to about 2 years. In response to growing climate concerns, there are two key solutions: adaptation and mitigation. Adaptation is a short-term solution that helps manage the risks, but oftentimes makes the problem bigger in the long term. Mitigation is a long-term solution that aims to solve and treat the problem. Looking at the circle to the left, an adaptation response to a habitat becoming unsuitable for a plant species would be artificially preserving the tree species so it doesn't go extinct. In commercial settings, the adaptation would be switching the type of plant species being grown.
Looking over at the circle on the right, we can see that two major examples of mitigation in the Pacific Northwest are carbon sequestration and improving on sustainable forestry. As we all know, high carbon emissions compose a major contribution to the greenhouse effect resulting in climate change, and in the Pacific Northwest, we have a great opportunity to act proactively to mitigate carbon emissions via carbon sequestration in our forests. Carbon sequestration, for those that don't know, occurs when carbon dioxide is taken into a plant and stored in its biomass. Studies suggest that we can maximize carbon sequestration by supporting the existence of forests that more closely resemble peak biodiversity and maturity to maximize niche utilization, which in turn maximizes forest productivity as compared to more homogeneous forests. In addition to supporting the growth of healthy and mature forests, by practicing sustainable forestry practices, we can also limit the amount of emissions produced by harvesting techniques, as well as the negative impacts of unsustainable forestry practices.
Now that we've outlined some of the risks that climate change poses to forestry, I'll be going over a few forestry mitigation tactics and covering why the Pacific Northwest is so important in this effort. So Oregon and Washington are home to more priority forest stands than anywhere in the western United States due to a combination of precipitation, temperature, soil conditions, as well as land use planning that has allowed for large forest stands. That is what this figure here shows. It ranks different areas in the western United States by their priority, and as you can see, Oregon and Washington have more high priority stands. So this is crucial when we think about using forest sequestration as a mitigation tactic for climate change, because the policy decisions in the Pacific Northwest on this subject have more of an impact than anywhere in the U.S. West. This chart shows the net present value of different policy initiatives for various U.S. regions, including the Pacific region. Net present value is essentially the future benefits of an action stated in today's dollars, and it allows us to compare different policy decisions and assess whether they're worth the cost. So for the Pacific Northwest, afforestation and reforestation are the most productive policy measures, followed by fire mitigation. One policy through which we can facilitate afforestation is through government subsidies. So an example of such a program would cost about $6 billion annually and would result in $90 billion in net present value due to future damages avoided through carbon sequestration. So the last thing that this graph shows is that reduced development had little economic benefit for the Pacific region. Another tactic is creating a market to allow productive revenue streams for landowners to practice afforestation called the carbon credit market. Essentially, greenhouse gas emitters would pay for carbon permits which allow them to emit 1 ton of CO2, which would be backed by an acre of afforested land which offsets that emitted CO2, sort of like a cap and trade program. Alternatively, you can accomplish this through a government subsidy per hectare reforested, and the benefit here is that you take away that market component so that this method is generally easier and quicker to roll out as you're not setting up that carbon credit market between industry and forest managers. So this is the crux of our policy recommendation here, that the timber industry transition to one where one of their forest products is carbon sequestration, and forest managers are paid to keep their trees in the ground.
The Homestead Act of 1862 allotted 160 acres to any Caucasian willing to work the land. African Americans were technically allowed to settle the land starting in 1866, but there were plenty of laws, like the Oregon Black Exclusion Laws, preventing them from doing so. This brief mention of racism-fueled inequality was, and sometimes still is, prevalent in policy in Oregon. The anthropocentric view of the world and our interactions with it have been employed in the last few centuries. Anthropocentrism is the view that humans are the only beings on Earth with intrinsic value, and all other beings and items have their value defined by the usefulness humans gain from them. As we move through the 21st century, we must rethink our interactions with the Earth and species sharing it. The biocentric and ecocentric lenses are lenses we must look through to do so. Biocentrism is the theory that all living beings have intrinsic value regardless of their usefulness to humans. Ecocentrist theory goes further to assert that the ecosphere has core value, and this includes, but is not limited to, geologic processes, the water cycle, the carbon cycle, and the nitrogen cycle. Looking at forests through an anthropocentric lens again, we see that forests provide a lot for humans. They provide water, biofuels, food, wood, recreation, climate stabilization, nutrient cycling, pest control, pollination, flood control, and other ecosystem services. Looking at forests through an ecocentric lens reveals that forests not only provide an economic value to humans, but they also have intrinsic value of their own. Furthermore, the forests have value to the entire biosphere, not just humans, and are a stabilizing force in the ecosphere. As a first world country, we owe it to the world to help mitigate climate change. Changes in forestry practices can help with climate change mitigation and adaptation. One way forests can help us tackle climate change is to use them to sequester carbon, which would mean that more forestry land in the Pacific Northwest must be dedicated to this goal. Earlier in the presentation, we discussed the value of forest carbon credits, which is a way we can help transform our economy into a green economy and allot funds to the regeneration of forests so that we can make a positive impact against climate change. We must also reconsider which types of trees we should plant to create these new forests so that they can survive and thrive during times of changing precipitation patterns.